Hello everybody, welcome back. We are still trying to write our kernel from scratch. Last time we've worked on locating and parsing ACPI tables, at least the root table, to get SMP going. As I'm still parsing the ACPI spec, I don't yet have a full plan in mind about where this is going. So today we are going to try finding the CPUs, the cores that we have on the machine. So let's get started. Right, so this is where we left off. Yeah, and I think I'm going to do a few things here. So this here would be, we need to check the revision. So if the revision is above 1, so if it's 2, then we take the extended whatever descriptor table, else we take just the normal one. Okay. So here we get the header, and from there we can go ahead and do the rest. So let's actually create here. So init from RSDT, I think. Just get that out of the way and do here init from RSDT. This returns nothing, I think, for now. And all of this goes here, I think. We need to pass it the RSDP. So hold on a minute. We need to pass it this pointer here. So even this maybe should go in here. And here we can just take RSDP address. Yep, yeah, that sounds pretty okay. So here we can pass it RSDP address. Cool. So now this is contained here. Very nice. So here we get this thing here. We need to check. Right, let's get started here. So we need to check that the header signature is equal to okay, so here I think it's about time I've created some sort of enum table signatures. So this would be an enum on a, so we have we know that we have 4 bytes for every single item of that. So I'm going to back that enum with a user2 for now. And let's actually add, so RSDT, I think. Hold on, let me open up the spec. There we go. So I think these are the ones we are going to need. Am I going to get all of them? I'm not sure, but let's try to get the ones that we want to work with first. So XSDT, and I think RSDT are the first ones. So let's put those in there. So RSDT would be, so here, how do we go about this? So .mem bytes as value. To value would be fine. So here we want this to be something like RSDT. We'll see if this works, but so RSDT there, and then XSDT would be the same. So this one here is, there we go. and then we'll see where we go from here. So here I just wanted to basically transform the 4 bytes string to an equivalent U32 enum, basically. So what we could do here is also pretty much the same. So std mem bytes as value. And this time here, there's no need to actually copy the bytes. So I think we can just tell it we want a U32 here and get that signature. And if this is equal to, so in from enum of, so table signatures dot RSTT. So if this works, then we're golden, I think. So let's try that first. So info got RSTT. Of course, let's do this. Otherwise, so let's do this here. Okay, so let's see if this builds. Oh, right. Oh yeah, of course. Of course. So this one here returns what? It returns a pointer to a value. So yeah, we probably need to do this. Okay. Access of union field pointer while field array is active. What? Okay, maybe so we need to do this. Yeah, it needs a slice there. And of course, yeah, here we forgot to specify that we want this to be U32. Whoops, U32. All right, so let's see here. QEMU, and yeah, let's get that started. Okay. Got XSDD, so that works perfectly. Nice. Very nice. So, let's now get to something else. Let's zoom in back here. And let's try to... so what were we trying to do? Actually, is there any need here to check this other than just validate that the tables are not wrong? So yeah, maybe we just want to validate that they're not wrong. So let's invert this. Yeah, so if that is different from that or mem bytes as value to U32 is of header dot signature, deref that, and then that's different from in from enum of tables or table signatures dot XSTT. Then we probably just return some sort of error. So I guess here we need to error. So hold on a minute. Bad signature, I guess we can just do that like that. Okay, so here we need validate checksum, right? So this validate checksum here should take a right, let's write that here. So validate checksum, and this here just takes a table, which should be a UA slice, and returns a Boolean. Hold on a minute. Is this the right? Yeah, I think we can do something like this. So it can get, we can run something like this, and it would either error and take us out of there, or we can just ignore that result. Yep, that sounds okay. So here the so let's think about for a bit. Here, what we need to do is we need to sum all the bytes, and they need to sum to 0, if I remember correctly. Okay, so let's sum all the bytes. And I think the summing should be should allow for wrapping, if I'm not mistaken. So let's take that into account. So var checksum is initialized to 0, or rather, hold on. Yeah, we should initialize that to 0. Okay, that's fine. And then we should go for, yeah, sure, for this to table.length. Can we do better than that? I think we can do better than that. If we do for table, doesn't that just give us a characters? Yep, it does. So checksum plus wrap equal to C. And here, if checksum is different from 0, return error bad checksum. Something like this. Yeah, okay, something like that works. Let's actually try that here. Okay, what did we do wrong here? Okay, so we need error union here is, this needs to be tried. So does this, and here if we go to main, to kernel main, somewhere over here we need to try that. Okay, still something else. Well, yes, obviously we forgot to actually pass the slice to that. So we have a header, so we want const I think we can just one-line that. So as many item pointer to uwait pointer cast of header. Header is a pointer. Yep, it is. I guess we should add const here just to avoid having to const cast that, and probably add a const here. And then to this, we take 0 to header.length. Because this is the length including the header, I think, so that should be okay. What's the problem here? Comp time in, of course, very nice. So this one should be a U8 still. Oh, right. So bad signature. This is not supposed to happen though. Checksum is 214. It's 1 byte checksum, so oh wait, no, hold on. Bad signature. What is going on here? So if signature is different from RSDT, oh, very nice. The classic. Okay, so we validated the checksum here and stop there, so that should be okay. Just want to make sure that we actually do get here. So I'm just going to test that. Okay, so we did actually validate the checksum. Cool. So now that we have this, we need to create actually a table from there. Or we don't really need a table. We know for RSDT. So hold on here. Where is it? Yep, there we go. So for RSDT, DT, and XSDT, we have so entries that are basically pointers to other tables. So either 64-bit pointers or 32-bit pointers. So yeah. So here's what we are going to do. So let's think for a bit. Let's create const. Entry type would be so if header dot signature actually hold on, let me just get this out here. So const header sig is setmem bytes as value of u32 header.sig. Okay, let's get that actually done with. So all right, that's fine. Let's do this, and this one would become header sig, and then here this other one would also become header sig. Cool. Let me zoom into here. Right, so if header sig is, or rather equals, int from enum of hold on a minute. So I'm going to actually yeah, never mind. I wanted to actually create a helper for this, but yeah, it's not too bad. So table signatures dot xsdt is of course. This one would become u64 else u32. Okay. So then const entries, this would be a mini item pointer of const entry type, sure, and then this would be a pointer cast of header plus header dot length. Oh yeah, of course. So actually, do we have something instead mem? No, never mind. I don't think so. So here I'm going to do pointer from int of int from pointer of header plus header dot length. This should be okay. And then here for entries, just going to capture one of those. And we are just going for now to do log debug found entry at something like this. Go on. And then this would be entry, right? No, right, let me just rename that. Cool. So let's try this again. Of course, we've messed up something. Incompatible types. Yeah, I should have probably kept the deref of that. Or maybe, since we can just copy that. Yeah, we could do that actually. There's no need to not do that. All right, what's the other problem here? Okay, so we need to have this be a comp time value if we want to do this. Okay. Fine. Fine. So how do we go about this? All right, let's window size, and then this would be add size of, sure, else add size of that. Here we are going to actually get rid of this. We're going to create w or window, sure, is statmem dot window, and we want the type to be u8. The buffer itself is what we just created here. Sure, but we actually are going to, so const entries, yep, this stays actually. This one here is const, whoops, const u8, and this becomes pointer cast, or rather I think it would still be better to do this from int of int from pointer of header plus header, whoops, dot length. Okay, so this one becomes entries and goes from actually hold on, let me just put that here. So this goes from 0 to header dot length minus size of header, description header, yep, that's the one. And this means we can just pass in entries there, and of course here we need to pass window size and window size here too. Okay, so what are you on about here? Oh yes, of course. Right, okay, fine. And here we can just go ahead and do const entries is okay, so I think I don't need this anymore. Okay, Very good. So here, whoops, it's the cold season and my hands are getting cold. All right, so let's call that a W, and no, before with that we need entry is, or rather, let's call it entry address. Sure. Yeah, actually, let's zoom into here. So here we need to do the reverse of stdmem. So thinking about this would be so bytes to value, sure, I don't care. And the bytes are W, and the type would be a yeah, so this here is kind of problematic. Because here we still need to decide if we want to group the 64, the 8 bytes or the 4 bytes. Actually, don't we have something here? I think we can just cast it. It's just a basic cast. But we'd still need to know to what. Okay, so hold on. I think we've made this a bit too complex. Let's do this. Function find rxsdt entries. Sure, for now, just turns void. And it takes 2 things. One is the header, I think. And yeah, so this one is a const pointer to description header, and then the other one is, I think that's pretty much all we need to pass it. Yeah, okay. So let's get here. So I'm going to also take this. Cool. Okay, well, let's never mind. Let's do if header sig is int from enum table signatures xsdt. Since this would be the most likely one first, then we can just do this, go here. We don't really need to do this anymore. We can just go ahead here and do 64 here. Yeah, that sounds okay. And that means that we don't really need this anymore here. We can just do entries, and this here would be the entry. We can just go ahead and do that. Cool. Of course, this one here is entry. So here would be else if header sig is int from enum table signatures rst, and we basically do the same here, except that this now becomes U32. Is this the single one thing we need to change here? And just in case. Else return error not our XSDT. It's quite bad signature. Yep, that sounds better, I think. So fine entries. This one takes header. I feel like this should also take header, since it's whoops, too soon. So table is that, and I feel like this should take header as a const pointer to description header. Okay. Of course, we've messed up things. Except one argument found 0. Fine. So this one would be here. This goes header, and this should just build. Okay. Incorrect alignment. Oh, yes, of course. Of course. So here we need to specify the alignment. So we need to type that this aligns to 1. So there's this one. Not sure if the header is guaranteed an alignment, but you know what? I'm just going to do this everywhere here, just so that the header type has an alignment of 1. I'll also do this here, just to guarantee that if we try to read the table, we don't fail on alignment constraints. Ooh, nice. Well, not nice, but okay, so we do have things, but we do also have a problem. We found a lot more entries than we expected for some reason. Okay, so here we must be doing something bad. So header plus header.length. Right, so log debug. So how do we go about this? We should probably write header at pointer to header, right? And entries at something like this. So this one would be header, and this one would be entries dot pointer. Oops, just entries pointer. But that also means that this needs to go, and this needs to be just that. Okay, well, still the same problem, but I think we will at least have some insight into why that is. So header is at this address here, 0E8, and how long is that? 36? Oh, yeah, okay. My bad, I guess. So this one would be size of description header instead of header.length. Description header. This one is valid because we take the full table. Yeah, the rest is okay, I think. Very nice. All right. Okay, we still have the same problem, but at least we have a few entries. Now, the main question is... Oh, I see. I see the problem here. So this here needs to be divided by size of U64. Same goes for this guy here at size of U32. What's the problem with this? Okay. All right, so we should be good to go here. Hopefully, and I think we are good to go. Yep, that looks very good. So we have entries there. That looks like the correct size. And then we have 5 entries. Very nice. So, now that we have the entries, we are going to actually try to put them somewhere. So hold on, let me think for a bit. All right. So at this point, do we have? I think we should have an allocator, right? So speaking of allocators, I'm almost done with the slab allocator, so that should be coming soon. TM. Right, so here, if we create something that I'm going to call ACPI context, sure, no, let's call it ACPI tables, and this would be an array. Hold on a minute. No, should probably be a stud enums enum map, I think, with the enum being table signatures, and this here would be ACPI table. Okay, let's actually do something here. ACPI table map. Sure. This one is enum map of table signatures and ACPI table, of course. And then this go on. This becomes ACPI table map. And of course we need that to undefined, otherwise it's going to complain. And somewhere over here, const ACPI table is a struct. This one doesn't need to be external because this one is managed by us. So hold on, let me think for a while. So what we are going to need to store is the header. The header is fairly small, I think. So we can copy it and store it inside this struct here. No problems, I believe. Yeah, it does sound like... Since we already know how many tables we are going to have, since our map is basically keyed to this enum here, we should be fairly safe on memory usage here. Okay, so we are going to copy the header. So this would not be a pointer, it would be the whole thing. I'd also would like to get a pointer, or actually an address. Okay, so let's do this, and let's do vert address the address, and yeah, let's do this for now. Let's just keep them numbers. And of course, we might want to do is valid, which would be a Boolean or something. So here we need to import arc, I think, which should be just from arc, and it means that this here would be arc.memory.paddress. Okay. So hold on, let me just make this a bit better, and let's think about how we want this to be. So I guess we can create an init function here that would basically take in a... So hold on a minute. From physical. So, okay, so this one would return self. Let's just call it ACPI table. I found myself liking to name things like this a bit more. So this one is init. The init one will take the address. No, actually, yeah, the init will take a header, a pointer to a header, actually. Descriptor header, const, obviously, and returns ACPI table. Otherwise, this one is it from phys in the cases where we don't want to go through this whole thing here. So actually, this is a good idea. Let's just copy this, get here p address as a arc memory p address. Does this one takes a p address? Perfect. So p address, you go away. V address. Yeah, sure. Let's call it address like that, and we can actually just go ahead and do this. Yeah, we can do this. So now I'm hold on a minute, let me just fix this. So address, you know what, table, or yeah, sure, table address. Okay, so here we get the signature. Here we don't need this actually. So that goes. And now what I need to do is so yeah, this here becomes const is valid, and this goes like yeah, I might have made this more complicated than it needed to be. So let's fix that quickly. So this one here becomes a Boolean. This guy here returns false. This guy here returns true. And if not that, whoops, we return error.bad checksum. That works out. That does work out. Okay, fine. So now we return something like this, and here we go. So physical address is p address, vert address is table address. So I guess we need to bitcast endcast that. Okay, is valid, is valid, and obviously the start of the show, the header is. So we need to might want to do mem copy. Hold on a minute. So let's do something like var table is ACPI table, sure, and here we can just do set mem. Nah, it's fine. Undefined, right, and here we can go ahead and do add mem copy. Yeah, we can get there. So destination would be table dot header, and source would be just header, I think. Whoops. All right. Okay, so this one here would be a lot simpler. Yeah, actually, let me just do something here. So, this one here takes a p address. Yeah, you know what? Never mind. Never mind that. I think we can just do this here. Return table, return init with header. Now we need to get the p address, obviously. So const p address would be so memory dot kernel vmem dot vert to phys of header of as v address. No, hold on. It's bitcast of int from pointer of header. Yeah, that should work. I think. Virtual address would be int from pointer of header. Yay. Okay, let's see how bad that is. So unused function parameter, of course. Yeah, we'll get to that in a bit. So we are going to need, okay, fine. We are going to need to use this for it to work. So here what we are going to do is ACPI tables dot or equals tables init. So wait, hold on a minute. Can we do set, or is it just read only put? We can put into there. So init, whoops, init Sure, I guess that's something. And here we should go ahead and start by actually putting these tables into the map first, right? So hold on a minute, let me think. Let me actually first remove that, and here we can go ahead and do ACPI tables dot put. So we need a key. In this case here, it's well, we don't know. So maybe we're going to do that here. Fine. And then the value is init that takes in the header. That sounds okay. Let's go down here, put this in here. This becomes RSDT, and let's see if this works. So still unused function parameter here. So just get that out of the way. And now the real problem. So expect type enum field struct, but found for, oh yeah, actually I forgot the this. So type is not an indexable pointer. Or a pointer to an array. So hold on a minute. I cannot specify a single pointer to be copied. So does that mean I can just do this? I think I can just do this. That should be okay. So here, yeah, I should just do that. It should be a copy. This here should be a copy operation. Okay, fine. All right, we forgot to do this here, but I should probably do log dot info initialized. Yeah, I can do this. Tables, and here we just do any, and we do ACPI tables. So just want to take a look at what we have in there. Okay, let's see. So we have one table. Hold on a minute. Oh, okay. So we have one table that we found. The other one would be the RSDT, which we don't have. So that's fine. That's pretty okay. So now let's move on. Let's move right on. Okay, so we have our entries here. We want to find out what table is that entry. So here we can do function so at this point we can just convert everything to U64s, even the U32 pointers. We don't really care about those. But let's actually let's actually take a type parameter. So here we want to read no parse table, right? So comp time t address type and char address t address. Of course, this one returns void, and it's just going to fill the tables in the other map. Right, so const header is pointed to const description header. This fine description header. This one is pointer from int. No, actually, no. We don't need to do this. We just basically need to call this with init from fizz of header of address. And if we even go further and do ACPI table is of type ACPI table init from physical with address, and we can just change this to ACPI table, and whoops, hold on, that's not what I wanted to do. ACPI table dot header dot signature. Okay, so here we do have a slight problem. So let me go to here, and we want to create public function from signature. Sure. So this one here would take a signature, should be a for const u8, right, and it would return table signatures. Sure, I don't need that. I just need this here. Right, so what we need to do is enum from int, of course with a return, enum from int, and the integer itself is the .mem bytes as value. I think we can just live with this. Bytes to value of U32 and signature. And actually, can I do this? I think that might be an okay idea to do that, but let's see. Fine, so here we were, and that means that this here would be tables, or rather from signature, ACPI tables.header.sig, and that should work. Of course not. Structure layout requires size whatever. Oh, okay, I can't put this in here, otherwise, yeah, my struct would be 4 gigs long. Oh, right, that looks pretty okay. Let's see here. Fine, so now we kind of need to call into our parse table u64 and entry, I think we call that, yeah. Oh, right, some more problems. Yep. Okay, that's fine. Let's see. Okay. Invalid enum value. That's actually nice. That means that we found a table that we did not have before. But what's sad is we don't actually have the actual value. So hold on a minute. Let's go and do log.debug.parsed table with signature. Yeah, sure, why not? Let's do something like this and do here ACPI table.header.sig. Sure. Okay, so we have FACP. So let's add FACP to our list of things here. So FACP, I guess. So I kind of want this to be generated automatically from a list that I can provide, because whatever we put here is the same that we have here. So it's kind of pointless to write them twice. But for now, let's just get on with it. So value u32, whoops, and FACP. All right, so next one. APIC. Right, so let me just do this and do FACP goes to APIC, the C. And actually what I want to do is, so this one panics. Yeah, it does panic. So you know what, let's just do this for now. Just gonna get the full list, add them, and then move on. Okay, so APIC HPAT. So APIC goes to HPAT, and so we need two more. So let's just do this. This goes to WAET. Is that it? Looks like it. And this goes, so HBET goes to BGRT. So I'm just actually curious to know. I think HBET is for the high precision timer. APIC is what the table that has the cores and interrupt handlers and stuff like that, or yeah, APICs, local APICs and stuff like that. This one I don't know, but I'm curious what WAET and BGRT are. So where are the tables? So APIC is this, that's cool. Boot graphics resource table, interesting. Where's the W, whatever? This here, Windows, yeah, don't really care. And what was the other one? HBET, yeah, so high precision event timer. Cool. So I'm just taking a look at this. Oh, cool. So that means that we can actually set a logo or something that gets displayed on boot. Huh. Interesting. Right, so now let's actually go and put our things into our table. Okay, and it looks like we have all the tables we need. So fine, cool. Right, so now next step would be to I think that for a pure ACPI stuff, well, first of all, I'm still reading the spec, so I still have a lot of things I don't know about or I don't fully understand, but here's my current understanding of how it works. So this is very hand wavy, but ACPI, advanced configuration and power interface, right? It basically lets hardware manufacturers define tables. So for static stuff, for static things, and also there's this thing called AML, which stands for ACPI machine language, which basically is interpreted bytecode. Sure, yeah. And this here, so if I do this, I think would be better. Yeah, sure. So for dynamic things, so basically what happens here is that either we have a table that describes a given thing, which is basically today we are going to look at the cores, since the cores are fairly static. So I'm not sure anyone expects to add new CPUs, basically hot plug in new CPUs. Although it can be possible with NUMA things, but yeah, I think on most consumer hardware, CPUs are fairly static things, so they can be described with a table. Otherwise, for things that are dynamic, so basically things like plug and play, so PNP, PCI, stuff like that, buttons on the computer case, lid events. So if you have a laptop and you close the lid or open it, stuff like that. Things like just thermal events, so something that overheats or basically goes from a thermal state to another one, etc. Right? So these go through this AML bytecode, and also what AML bytecode allows us to do is device enumeration. So basically we can, device manufacturers will have different ways to enumerate devices, or how they are structured in a sort of bus structure. So we can have a root, and under the root we can have some level 1 device, so something like a PCI bus, or we can have a, I'm not sure, but something like a memory controller or something, stuff like that, right? So, and under this PCI bus, for example, we can have like device 0 and etc., right? So this structure here is also described by AML, because AML is basically an interpreted bytecode, so it has opcodes for object creation and this basically lets us create a hierarchy as well as basically methods. So it can define actual methods that need to be run. And for example, when you receive an event, the event will let you or ask you to, or rather, the spec will ask you to run a given handler. So if you receive an event from general purpose events with some code, I'm not sure, but some code 0x02, for example, you need to run some event handler like trigger 02 or something. So this is my current understanding of how this works. The way I see it is we need to, or rather, let's talk about plan, how this needs to work. So first, tables. So load the tables and do the parsing. So that's what we are doing today. Then we need to create a namespace. Namespace is basically this. So it's a tree structure that has a single root and that has a lot of devices, a lot of objects, air quotes, AML objects, and objects can be packages or devices or like memory regions or stuff like that. So yeah, create a namespace, and then the other step rather is to load. Again, I'm just going to use codes here because these are the terms that they use. Load the namespace, and by create, they mean actually create the namespace structure and add in the default objects that are specified by the ACPI spec. And then loading the namespace means parse all the DSDT entries. So this is the differentiated something subsystem, whatever, description table. And there's another one called SSDT or something, but you parse those entries. You basically get AML blocks, so that gives you AML bytecode blobs, basically, and then you execute or you interpret those to actually do things, so apply actions on the namespace that you've created here. So basically, create new objects, load new objects from namespace, get the values, do operations, stuff like that. So in my mind, this would be the plan to create an ACPI driver. The problem is that this here is fairly complex, and I don't think I have the facilities to test this. So it would be very hard to test this on a virtual machine. We will probably need to make a separate library just for this and have a bunch of synthetic tests for it to work somewhat correctly. So I'm not really sold on doing these two steps. If needs be, we might want to use an external library, but we'll see, because from what I see in the spec, these two things here will require a lot of work for absolutely no return at all. And so, yeah, we'll see. Main things we are interested in might be device enumeration, some buttons, stuff like that, so that we can handle shutdown, power off, sleep, hibernation. Oh, I forgot, and this is for the config side of things, but there's also the power side of things, which basically ACPI handles with huge air quotes. So power states, or rather, by that I mean that the ACPI allows the kernel to transition into power states. Basically, the kernel will stop talking to the devices, and then it's going to ask the ACPI to tell the hardware to start shutting things down, to sleep or something like that. Right, so I feel like a lot of yapping happened here. I think most of it will be cut in the edit, but I feel like the best way to understand something is to explain it to someone else, and that's why this channel exists. So yeah. Cool, nice, very good. So now I think we are done. Not really done, but I think we are basically we can move on from this, right? So let's actually create a new public function here. Where are my public functions? There we go. So public function. So hold on a minute. What I want to do is parse a table, right? Actually, hold on. I might have. So in it from RSTT, sure. RxSTT. Wait. RxSTT entries. Good. This one here is parse table. Okay, that's good. So iterate table. Okay, so I'm just trying to explore something here. So this one returns void or some sort of error, right? And this here takes a few things. So first of all, it will take an ACPI table iterator. Table iteration context. So context would be this, and then it will also give a table. So this one would be table signatures. That's fine. Now, let me try to explore this thing here. So ACPI table iteration context. This one is an enum. Hold on a minute. It's a union based on table signatures, right? And for APIC, we set, hold on a minute, I forgot, this is this. For APIC, we set APIC iteration context. Right. And here we can go ahead and do epic iteration context. This one would be just a struct, I believe. And this here will basically have. So the way I'm thinking about this, first of all, let's take a look at epic. Right. So multiple epic description table, a lot of yapping there, and then here we get to things we are looking for. So we start here. So we have the local interrupt control address, and this is here the 32-bit physical address at which each processor can access its local interrupt controller. So basically, at this address here, each of our cores will have access to its local epic, basically. Flags, some flags, I guess, and interrupt structure, control structure. So list of interrupt controller structures for this implementation. Right, and if we get to these, we basically have processor local epics, so IO epics, and what MADT is interesting for is for if you have a supercomputer and you want to plug and play new blades with CPUs and memory and stuff like that. So basically you plug in a new one or many NUMA nodes, then this you get an event for that. You'll call you get an ACPI event that tells you that there's a new device. You'll enumerate that device. You find out that it's a processor or an IO object, and then you call MADT on that to get these structs, and then you can get started from there. As far as we're concerned, we're just going to use the table. The table has the fixed value, so whatever the computer has started with. So that's what we are going to use. Okay. Right, so here we can go ahead and get into the details, but as far as I'm concerned, what I want to do is for each of these things that we have here. So we'll see which ones we skip. I think we are going to skip the RISC-V ones and these ones here. But for each of these, I'm going to create a sort of callback. So this here, it's going to have, so forgot the first one. So local epic, and this here would be a pointer to const function that takes some sort of any opaque, right? And I'm not sure that this is a good idea, but just going to try to explore it for a few minutes here. So takes in some sort of description of local epic. So local epic specific stuff, right? Here we can go for IO epic, and then this goes same thing again. Any opaque, and here some specific things, and of course here we need to take a pointer, which is an any opaque, which should be the base of our context. Right, so the idea then would be we try to find the table first of all. So const table is ACPI tables dot get I think we can just get pointer const. Yeah, we don't need to modify the table itself. And of course the key is stable, right? So does this fail? No, but we can get a null thing. So if table, right, let me just rename this table opt. Same goes, whoops, table opt, and this one is stable. Okay, so, all right, you know what, let me just remove this for now. What is the problem here? Expect return. What? Oh, yeah, of course. I don't expect you to return anything though from that. Cool. Very nice. So here, table. We want to switch on context. And if we find epic, no, hold on. First of all, we want to make sure that the contexts, first of all, let's do first things first. So error, table not found. Okay, that's great. And then here we'd like to match the context to the table type. So how do we go about that? Context dot, is there like union? No. How do we make sure that the table and the context active enum field are the same? Yeah, I'm not sure about this. So for now, let's just move on. Okay, so I want to switch on table dot header dot signature. No, hold on. Const table signature is actually never mind. I think we can just switch on table. So if we have epic, we get the no, that's fine. If we have epic, then we go ahead and get const epic. Hold on a minute. Const MADT entries. Yeah, sure, we can do this. And this one would be a many item pointer to. Now the problem is each of these interrupt controller structures so how are they? Yeah, so they have different lengths. Yeah, they have different lengths. You have 8, 12, 10, 12, 8. Okay, so we are going to actually yeah, so const u8, sure. And then this would be table. Ooh, I might be in trouble here. T, or rather, hold on. This one here becomes sig. Yeah, okay. I'm not in trouble anymore. So table.header dot or rather table.virtual address. But first of all, if table is valid, or if it's not valid, then return error dot not bad checksum. Sure. Okay, and here we get the virtual address, right? And to that we add a size of, yep, okay, fine. Let's actually call this cursor. And then this is just a pointer to const u8. Yeah, that looks okay. So this one is description header. And of course, this whole thing needs to be a pointer from int type situation here. Okay, so we have a cursor that's going to point into different, I guess, fields in our MADT structure. But first of all, const MADT is, I think we should create that here, pointer to const ACPI epic. Oh, this is going to get, yeah, MADT, that's okay, that looks pretty okay. Pointer from int, or rather, pointer cast of cursor. Yeah, okay. Now, let me move these up here somewhere. Where is, there we go. So this one here goes here. Just going to do this and rename this ACPI RSTP. Sure. And I'm just going to actually RSTT, just make all of these lowercase. Yeah, so XSTT. And you know what? Let's just do, yeah, there we go. And we'll deal with the other problems in a bit. Fine. So now this here also needs to get that treatment. Nice. Okay, good. So const ACPI MADT is an extern struct has a so thinking the thing I'm thinking about is, do I skip the header? Because I know that MADT is basically this exact header that we have plus these fields here. So it might be, yeah, actually, you know what? I'm not skipping the header. I'm not skipping the header. I'm just going to keep it. So header is a description header, and of course we are, I think this one is already a line one, so there's no need to tell it that it should be. Then we have a local, so lapic address, which should be u32. And then we have flags, which should be some sort of u32 also, but okay. So flags is a back struct that has pcat compat, which is a u1 rule, maybe, and it has a reserved U31. And of course here we can specify it's a U32 backed struct. And of course here we need to type this is aligned to 1. Same goes here, align that to 1. And of course, what's the other thing? Here it's an array of interrupt control structures, but since we don't have variable length arrays in Zig, we're just going to not put that in there. So let me just actually interrupt controller structure, interrupt controller structures beyond here, up to header.length. Sure. Very nice. So now I can just do this actually and do pointer cast on header table dot virtual address actually, and we can do pointer from int. That sounds pretty good. So now that we have our MADT, we should actually go on and do so hold on a minute. Hold on a minute. Okay, so here actually let's just switch context. Here we get epic. But first of all, we need to make sure that our signature is, if our signature is different. Hold on, how do we compare signatures and stuff like that? Yeah, so we need to do this, and then we compare. But we already have a signature, so we can just compare them, right? Yeah, we can just compare them, I feel like. So if this one is different from table signatures.epic, then return error bad context. Okay, that sounds pretty good. Now we have MADT, and now we also need to capture our context as epic context. Right. So here epic context dot lepic address would be MADT.lepic address. Yeah, I'm not sure about this. Lepic address, sure. And then we do epic context dot has, and I feel like we should probably make some of these things here optional. So if epic, no, never mind. We can just call them. Actually, yeah, I see where I'm going with this. So here we are going to need public function lepic address, right? Lepic address, and this one takes self, which would be a pointer to epic iteration context, maybe a const pointer, who knows? Yeah, we need a const pointer at least. And we take also a address user2-bit address here. This returns void, and then this calls lapic address, which is a const function, takes in any opaque, and a utility2 returns void, and then we can go ahead and just do self dot lapic address, self dot pointer, and address. I feel like that sounds pretty okay. Const function. So let's call this has. So I just need to understand this. So I guess this is for pick. For the older pick modules. So I just need to make sure that this is actually, so Intel this. Yeah, so this one is for the older pick chips. Okay, so let's go has pick pick yeah, pick needs masking. Sure, I'm not sure about how to go about that, but for now, so a pick iteration context, and I guess if we get called on that, then we need it. Otherwise, we don't. Sure. Pick compat, and then this goes self dot pointer and true maybe. I don't really care. So pick compatibility is const function takes in any opaque, and a boolean returns nothing. Okay. Fine. So this one has peak needs masking. Sure. So if MADT.flags.that, get that in there. Cool. And of course, obviously this, so lapic address. So hold on, why does this not want to, what is the problem here? Okay, fine. So does this, yeah, so it's marked as unknown. Why is that? Oh, we need to use this somewhere. Fine. So let's actually, yeah, I'm gonna need to go here, create smp.zig, sure, fine. So const ACPI, and I might want to split this into two packages, but for now, let's just move on. Right, so here, let's get rid of that. I want to actually sort of call this pub function init short void. Fine. And here I want to create actually hold on a minute. So yeah, let's just do something simple. So const MADT iteration context is a struct, sure, and this one has nothing actually. Const log is stud log scoped SMP. Of course, we need const stud is import stud fine. So this one here has a few functions, and then the main function here would be public function ACPI context. no, iteration context. This returns ACPI dot, and of course we need to go and mark those as public. Public. Cool. So ACPI iteration context, this one is ACPI table iteration context, and here we return. Can we actually do this? Yep, we can. So epic is, and we do something like, yeah, sure, why not? Here we can do lapic address is on lapic address. We probably could have made this a lot easier on ourselves by, instead of going for something that's fully defined like this, we could have just went for, hold on, let me just explore this for a bit. So copy this here, put that there, and here we can do so callback. This one would be a const function, takes in any opaque, and then takes in a token, right, of some sort of type, and then it takes in arguments, and then this would be any type, right? So maybe this can be a, yeah, sure, something like this, const UA. That's actually okay. Whoops, come on. And then here we get the pointer, so any opaque. And that means that now it's up to, yeah, return except expression here is this, but now it's up to the implementer of this to actually have, but they need to know, we need to agree on tokens. So, but I feel like it's, yeah, it's a bit more future-proof than what we have here. So I'm just worried about this args here. I feel like we want to have some sort of, yeah, we are going to need to pass some sort of anonymous struct or some sort of tuple or something, and depending on the token, it can be interpreted some way or other from the other side. So hold on, let me actually go and move on with that just for 1 second. I'm just going to vibe with that. So this one is pointer is self. Obviously, since this one is going to take self as a pointer, maybe a const one. This one does not need this to be not const, so yeah, okay. And then this goes to MADT iteration context, sure. And then, as I said, callback here would just be on callback. And then we just need, yeah, of course, I forgot that this is not a oxidational language. Right, so just function, I guess, on callback takes in a pointer, any opaque, and some sort of token. For now, let's just assume it's a slice or a string, and then some arguments of any type. Let's see how far this takes us. And here we are just going to do log debug on callback of token and whatever that type is. So token and args, feel like expected. Oh, hold on a minute. My bad. There we go. So what is the problem here? Unused function parameters. Sure. So, is this a good idea or is it just... right, so this one here goes like this, just for now. We don't need to switch on context anymore. We actually can switch on signature. That means that this, we don't really need to do this anymore. We don't really need to do that anymore. And we can just actually go ahead and do context dot callback. And we can just set, hold on a minute. So notify, sure, we can do something like this. This one would be lapic address and sure, notify, then this one would be big compat, and then this one would be true. Or maybe you can send void. Hold on a minute. And here we need to go here and do public function notify takes in self, a pointer to const, ACPI table, whatever that is, and returns void. And it does self.callback, self.pointer with token and args. So that needs to go here. So token is const28, not 78. And args, I think, is any type. So I'm not sure about the any type thing. We might actually get surprised, but so I'm not sure if we hold on a minute. Can we actually do comp_time t type and then args of type t? But that means that here we need to actually tell it what the type is, and that's a whole thing. So yeah, for now, let's just do that. Okay, let's try to build this. Of course, we need to call. So go to main and do try. Of course, we need to import that. So this one is what SMP, I think, and then this one is SMP also. SMP.init. We don't need the try, I think. So we do this. Wait, hold on. Did we not call that? Yeah, fine. Very nice. So this one here is ACPI.iterate table with a signature of epic. Very nice. And a context of so const mad iteration context is MADT iteration context. Okay. And And then here we can do something like MADT duration context dot that. And this here, okay, so now this needs to be tried, this needs to be tried, and this needs to be tried. And here, of course, we are going to get a few problems. So no field name pointer in enum ACPI table signatures. 49 in ACPI 49, I think. What? Oh, right. So this one goes then. This one is just a struct. So no field named epic in. Okay, so 122, 122, and this one becomes epic. All right, now let's start by looking at the actual problems. Switch must handle all possibilities. Very nice. Else unreachable. Good. Okay, so now we are going to start getting the problem. So 53. 53 here. This needs const. The rest should be okay, I think. Except expected pointer to const found. Okay, sure. So that's SMP here, and this one here needs to become const. I don't really care about that. Okay. And yeah, so we have set that to print. So let's figure out what we need to do. Ooh, failed with error table not found. But actually it does work. There's something there. Okay, so I'm just going to get rid of this because that's kind of bad. But there's something there, and I think it's going to be a bit more flexible than the other stuff. Right, so here, return. Yeah, that sounds pretty good. So here we just return, and now we can get our cursor back. Except that this time here we need to create the cursor from table plus ACPI MAD. Yeah, MAD table. Whoops. Let's get that there. Very nice. Okay, cool. So we're almost there. TM. Now we have our cursor. It's a cursor to constituate. So how do we know what is what? So how do we distinguish the these things here? So do we get something here? No. So I guess we just rely on. So from what I'm seeing, all of them have 2 bytes at the start that define the type and the length. Yeah, so type length, etc. So I think we can go ahead and do. So I'm just going to go here. And in here, I'm just going to define a const mad. So how do they call these things? Interrupt controller. interrupt control. I'll need to interrupt controller header. Sure. This one is an extern struct. Fine. So this one has a type, which is a U8, I believe, and then a length, which is also a U8. Okay. So that means that here we so while cursor is less than, let's also create here const. So this one becomes variable, this one becomes a constant, and then, so hold on a minute, just thinking. So table end is pointer from int of table vert address plus header dot size, or table dot header. I can do that dot length. Very nice. So here, instead of just having a cursor, just going to call this a interrupt controller header. So this one is a const. ACPI MADT dot interrupt controller header. Sure, that sounds pretty okay. So while interrupt controller header is less than table end, and obviously we do interrupt controller header plus equals interrupt controller header dot length. Is that valid? Have a known result type, that's fine. Const U8. I hope they don't look at types when comparing pointers, because that's pointless. Right, so when we have this, we basically want to look at the type. So switch on interrupt whatever dot type. And obviously here we need to go ahead and pick up all of these. Okay, fine. So hold on, do they end at 7F? So wait a minute, is it an I8 instead of an U8? So 127 instead of 256. But I don't think it changes much for us. So let's go ahead and change this to so thinking, and we can go ahead and do const. We can put it inside here. So type is an enum backed by U8. I think that doesn't change much for us. And then here we can probably just do type. Very nice. And here we can go ahead and can we please just copy these and do something with them? Hopefully it's not horrible. Oh, it is horrible. Nice. So, okay, first of all, let's go ahead and do arch. Okay. Oh, right. Okay, so here, let's go ahead and do, so if it doesn't start with a digit, just delete that. Right. Okay, I'm not sure why 0 has not been considered a digit, but fine. Let's get that in there. So now that we have this, I'm just going to remove this last one here and add this instead. And then, oh, but I want the names. You know what? I'm just going to do this by hand because, yeah, I can't be bothered actually. So, processor local epic is 0. IO epic is 1. It's fine. So actually, let me just speed run through this and be back. Okay, that just took a few minutes. Now let's move on. So where were we? We were about here. We needed to switch this. So I'm just going to do this unreachable to start with. And then for now, let's also do else unreachable. Oh, let's actually just panic on this. Unhandled interrupt controller type. Okay, and let's see if this actually builds. Okay, it does not build. So incompatible types. Okay, fine. It's kind of pointless, but okay. You know what? Since this is just U64 here, just going to get rid of this, and I'm just going to hit this with int from pointer, and yeah, that should do it. Hopefully. Okay, looks like it. Now. I should just run this, and it should just absolutely panic. Cool. Very nice. Now, just before we do this, I'm just going to log.debug.found MADT interrupt controller with type T. I think that's a new format for enums, right? So interrupt controller header type. Oops, build this first. And then we should be able to run that. Processor local epic. Very nice. So let's start with that. So processor local epic, and we do something. Not sure what yet, but we do something here. So now I guess we are going to need to create all these nice structs. So processor UID, okay, epic ID, some flags. Okay, fine. So processor UID. So let's go to MADT, and here this kind of sucks. This kind of sucks, and why is my thing? Yeah, okay, fine. So let me just redo this. And I think now is a good time to just move these ACPI sort of things out of here. So let's move this to acpi.zig in Falcon, so in the library, should say. And here we can just go ahead and take pretty much everything that's just related to the spec, since we know that that's fairly agnostic to what we are doing. So all of this goes. Sure, this one goes here. Of course, we need const stud is at import stud. There we go. So do we have? Oh, of course, here we need to get const ACPI types is at import Falcon.acpi, but now we need to go here and do pub const ACPI is at import ACPI.zig, and hopefully here we should have some tests, or not, but yeah. So ACPI types, what is this? This is a this, and now we need to go ahead and mark all of these as public, as things should be. And of course here we need to go public, public, and public. Whoops, bit too bit too eager there. Okay, cool. So now back here, fix this ACPI types. Sure. Types here, and same goes to this ACPI types. Same goes here, and same goes here. Some other problems here. Yep. Okay. Yes. Yes. And yes. Yes. And yes. This one too. And this one too. All right, so we should probably just have done this on all of them without thinking too much. Fine. So now I'm just going to build this, make sure that, oh, nice. So what is this? Expect const found u8 again. I feel like it just worked. But found u8. Okay. How does that work though? So that's here. Yeah, well, how come this worked before? Now it just doesn't want to. Okay, you know what, let me just rebuild this. Just take a look at what they want here. So they want a pointer, but they get a u8. Okay, so maybe there's... Okay, fine. I could have sworn that it just worked like 2 minutes ago, but maybe we just got saved by this panic here, and the second iteration did not go through. Okay, fine. Fine. Right, so what they want us to do is something like this, and maybe like so pointer what am I trying to do? So pointer from int of int from pointer of that plus this. So interrupt controller header plus whatever that is. Now, what is the problem here? Explain. What? Oh, yeah, of course. Cool. Very nice. Let's see here. So we should get a second, maybe even a third. No, okay, so we get IO epic and then we now die. Cool. So we do IO epic. Okay. So why is this not working anymore? Type. I'm just trying to avoid collisions here. Okay, fine. So what did we want to do here? We wanted to actually do something with this thing. So we want to go to FLCNOS ACPI, right? And we go somewhere over here, just after this, I guess, and we can create public const, and now we can go ahead and do processor local epic, but please keep this here. So struct, or rather extern struct. Yeah, sure. Okay, that's fine. Now, what do we have in here? We have the header again. So header is an interrupt control header, sure. That has an alignment of 1 already because, yeah, why not? And then here we can go ACPI processor UID. So processor UID. Hold on, how big is that? Oh, U8. Line 1 is trivial there. ACPI ID, let's say U8 again. Yeah, and flags. Flags, which is a sort of backstruct over U32, I believe. And then here we have so enabled online capable, and then reserved, I guess. Is that all? Yep, must be 0, that's fine. So now let's actually also go ahead and create the IO epic. So basically the same things. We have an ID, then, okay. Okay, a lot of hard work, but sure. So const processor local epic, which is a const pointer to ACPI types.acpi mad.processor local epic is pointer cast of interrupt source header. Fine, and then log.debug, and then we just dump that in there. So processor, whatever, local epic. Yeah, sure. Let's do local epic here. I'm just going to copy the exact same thing here. This time here, this goes to, whoops, come on. This goes to IO APIC. Sure. All right. Let's see if we are. Alignment of 4. What are you talking about? Okay, you know what? I'm just going to go here, and we are going to do it. We are going to do this. So this one is backstruct, that's fine. This one is a backstruct, that's fine. This one here gets in the line of 1, that's actually fine. This one gets in the line of 1. 1, 1, 1, line of 1. Same goes here. 1, 1, this goes there, this goes there. Yeah, okay. Sure. Okay. Okay. And yep, so this one gets that, this one gets that, and this one gets that. Of course, we forgot something here. Yeah, I forgot these two, so this one gets it, this one gets it, this one gets it. So does this one and this one. Let's see here. Okay, so hopefully, so local APIC, yeah, sure, we get a length of 8, and then we get APIC ID of 0, enabled true, online capable false. Okay, and then we have a local APIC, processor UID is 0, APIC ID is 0, flags enabled false, online capable false, and reserved. We don't really care. And then we get interrupt source override. So let's get to that next. So interrupt source, I'd love some help there, Mr. ZLS, but it's okay. All right, so again, I'm just going to do the exact same here. You can see that we're not calling the callbacks yet because I don't feel like it. So in source override, sure. And this goes interrupt source override. Sure, what's the next? I kind of feel like, yeah, okay, I'm doing it. I'm doing it. Continue. I am going to do that because I don't feel like doing this step by step. Cool. So let's run this and see. Okay. Let's see what we get here. So hold on a minute. Hold on a minute. Oh, I don't see the ones that are not handled. Fine. So log dot warn, sure. Unhandled. What's these? So interrupt. Interrupt. Controller. Type. Sure, and then we do interrupt controller type, of course. Let's do this again and run this again. Okay, cool. So let's take a look at these ones here. Warning, so we just have one other one that needs to be handled, I think. Just have one single warning here, which is a local APIC NMI. Right, so here we have local APIC what is this? Interrupt controller with type Okay, fine. They all print this. So IO APIC, fine. Interrupt source override. Cool. Nice. Okay. So let's see here. We have local APIC here, IO APIC, interrupt source override, interrupt source override, and that's all. I feel like we should have a few more things there. Yeah, I feel like, hold on. So, hold on a minute. How do we specify? Is that like this? No. Yeah, I forgot how we should specify. So hold on. QEMU CPU count. Can we please just get that? Argument. Okay, very nice. Can't we please just get this dash CPU? Right, so CPU. CPU. Okay, so SMP cache topology levels. Yeah, this sounds somewhat like what we want, but we also, okay, so this is what we are looking for. So SMP 8, for example, just okay, so I guess that's all we need to do. So it was just SMP 8, and now we should probably be able to see a few more. Yeah, there you go. So we have a few more CPUs here. So local APIC, you zoom into this. Local APIC here with ID 0, 1, 2, 3, 4, 5, 6, and 7. So we have 7 cores, and we see all of them here. Very nice. So now we can actually get to doing some SMP. And obviously, we should also have for each of those, there we go. So this one here, so the IO APIC, and here, wait, no. Hold on a minute. Might be missing something. Where is the address of, oh, this one here. Cool. So local APIC address is the same for all our cores. We don't have any override to that. Otherwise, we'd have seen local APIC address override or something. Is that something that we have? Or did I just hallucinate that? Yeah, address override structure. Yep, so cool. Very nice. So now we can get actually started on doing our things. Right, so the plan here is we go to SMP. Here we implement things that will look at the token and do stuff with the arguments. And then I think we should also have a token that basically says we are done parsing this table so that we can actually know that we can initialize our systems. Once that token is received, we can actually bring up the SMP or all the other cores and stuff like that. So we can start working on SMP properly. Right, so I think that's the plan for next time. Well, that's pretty much it for this one. We have worked on MADT entry iteration. As always, if you like this type of video, hit like, subscribe. If you have comments, remarks, or you just want to say hi, leave them in the comments down below. I appreciate those very, very much. I hope to see you next time. Fucking out.